Okay, so again, this is chapter 10 in your notes, and we're talking about waves. We're talking about these kind of waves right here. We'll learn more about transverse and longitudinal waves. Unfortunately, we're not going to learn too much about these waves, but you know about them, right? So we're talking about waves in science. It's a transfer of energy. Okay, that's what a wave is defined as in physics and in science, a transfer of energy in the form of some disturbance, usually through a physical medium. Now I say usually, there's different types of waves, obviously. There's two main types, and we're going to talk about the mechanical type waves that travel through a medium here. And so we're talking about traveling through air, and that's where sound is going to come in, because sound waves travel through air. They also travel through other material, but when I'm talking to you like right now, you're hearing that because my vocal cords are vibrating. Okay, that's the disturbance that I am creating in my body right now, and that vibration is coming out of my mouth, and my lips and tongue and teeth are forming the disturbances into recognizable sounds that your brain is interpreting. And so it's kind of cool. So that's where sound kind of comes in. A physical medium, other common ones, water. You can actually hear things in water, right? If you're diving underneath the water and you sit under there for a little bit, you can hear things and people moving and all that sort of stuff. And through a solid as well. Sound travels really fast through dense solids. Yeah. All right, waves are all around us. If we talk about waves, it's not just the pictures that we saw earlier, but some are visible, like water waves and ropes and slinkies and etc. So some are visible and some are invisible. So if we're talking about radio waves or microwaves or radiation, these waves are not visible. Okay, they're not in the visible spectrum. And just as a side note, microwaves, we have a microwave in this room, and a lot of you use that at lunchtime to heat up your lunch. And it operates by generating waves, microwaves. And those waves kind of travel through your food and excite the water molecules in your food. And when the water molecules start to vibrate a lot, they generate heat. And so that's how your food is heated up. I don't know if you've ever noticed, but something with more water in it, something that's more moist, will heat up quicker in the microwave than something that's super dry. And actually, something that's super dry, it won't heat up so much, and you think you need to put it in there for longer, and that's when you might start a fire because all the vibration with the particles. Anyways, so that's what a microwave does. All right, so most waves originate from a vibrating source. So when we talk about sound, again, like I say, my vocal cords, there's air passing through my vocal cords, and that's the vibrating source that generates this disturbance. And that disturbance kind of bumps like balls on a pool table. You ever played pool? Where one ball bounces into another, and it bounces into another, and it bounces into another. If you think about air as molecules floating around, the disturbance that I'm causing is bumping those molecules, and they're actually, that disturbance is kind of making it all the way through the air to your ears, and you're hearing that. So a vibrating source. The sources are often vibrating too fast to see. Okay, we study objects that we can see vibrating slowly or in periodic motion. So when we're going to talk about waves here, we study the objects that vibrate slowly and express and show periodic motion. Okay, so if we talk about a slinky or something like that, even if we shake that really fast, that's still fairly slow compared to the vibration of vocal cords or the vibration of speakers that are generating sound. Anybody know what periodic motion means? Sorry? Intervals? Okay, close, yeah, kind of close. Periodic is something that repeats, comes often. So it's like a cycle that repeats. So the same thing comes at certain intervals. If you could use that word. But yeah, periodic is basically repeated motion. Okay. The periodic table, we're going to study the periodic table of elements, right? It's called periodic because patterns repeat as you kind of move along the rows and up and down the columns. There's patterns that repeat over and over. So periodic motions repeated at regular time intervals. So there's repeated at regular time intervals. Okay, when we describe the motion of a vibrating object, one complete oscillation, and this oscillation word, maybe that's a word you've never heard of before, but one complete oscillation, that's like a one complete rotation or one complete kind of back and forth motion is called a cycle. Okay, it's called a cycle. So here I have my trusty fan. It's getting to be fall outside, so I don't need it as much anymore. But if you take a look at these fan blades, and maybe, just maybe I'll do something fancy here. What am I going to do? There it is. Let's see if this will work. Maybe not. All right, so here we go. We got the fan, got the blades there. You see that? And if I just touch this, I'm going to touch the on button here just really quickly. Just going to get those moving a little bit. Okay. If I get those fan blades around one complete time, where one fan blade goes all the way around and reaches the exact same position, that's called one cycle. Okay, but that's one repeated motion. Okay, so here, a lot of cycles happening right there. Right, a lot of cycles. Can you count them? No. Yeah, there's 1,000. No, I don't know. Just guessing. Anyways, you guys cool now? Yeah, you guys need to get cooler. There you go. Okay. So, the number of cycles in a given amount of time is called the frequency. The number of cycles in a given amount of time is called frequency. So if you saw those fan blades, if they were moving really slowly on speed, well, let's say speed 1, still pretty fast, but that fan blade is going around and round at a certain speed, right? And so it's the number of cycles in a given amount of time. If we could count the number of cycles in 1 second, so that is how many times that fan blade would go around in 1 second, that would be the frequency in hertz. So let's say we were able to count that on speed 1. And in 1,001 seconds, let's say it went around 37 times. So the frequency that the fan blades would be generating, one blade, would be 37 hertz, or 37 cycles per second. So hertz is the unit that is used. Okay? And the symbol for hertz is capital H Z. Hertz. Okay? So on speed 2, obviously the fan would be moving faster, right? It would be spinning around faster. So we would have a higher number of hertz, a higher frequency. So let's say speed 1 was 37. Let's say speed 2 is 85. 85 cycles per second would be 85 hertz. That one blade would be passing by. Now there's 3 blades, so we won't get into that. And then of course speed 3, you could have maybe 170. I don't know what it would be. Probably wouldn't be that much, but you see where I'm going with that. Okay, so we talk about crests and troughs here. Well, let's say we're looking at a wave that looks like this, okay? And this is a typical kind of wave. If you look up pictures of waves in physics on the internet or whatever, you'll get this, right? And it kind of back and forth, flips up and down and so on like that. And this is a repeated motion. You can kind of see that if we start here, if this is our arbitrary starting point right here, it goes down, back up, and then back down, and this is the start point to the next cycle. So this would be one complete cycle right here. See that? All right, so a crest is the high section. Here's a crest right here. B is the crest of the wave. The trough Okay, now a trough, maybe you know the word trough from like a feeding box, right? If you know anything about the animals and they maybe drink out of the trough or eat out of the trough, it's sort of this lower part right here, right? So that's a trough. An eaves trough, okay, shaped like this on the edge of your roof. So that's a trough right here. See as a trough. Okay? Now, A here, so I've got the answers kind of down here as well, so I'll flip those up. But A, this part right here, okay, from any part of the wave to the next sort of identical part of the wave, that would represent one cycle, or we call this a wavelength. Wavelength. So it's the length of one complete cycle. So every cycle will have a wavelength, and obviously some of these, because there's so many cycles, if you think about that fan, right? Okay, if we were graphing this, the position of the fan blade, this wavelength would be really, really small, right? The length it would be really, really small. So if you have a lot of cycles, the wavelength gets shorter and shorter. So consider this. This is a long wavelength, right? Here to here. This is a short wavelength. There to there. Very short. Okay. All right, so amplitude is the last thing. Actually, I guess D was the crest, but this is the crest. B here is this distance, which actually is the amplitude. Okay, so the distance from what would be rest position or the middle of the wave, the distance from the middle to either a crest or a trough should be the same. That is the amplitude. The amplitude. Okay. So generally, a larger amplitude of frequency and wavelength is the same. That means kind of a louder volume with sound and stuff like that. So a higher amplitude is just a little bit more energy. See, up a little bit higher, down a little bit lower, greater amplitude. Let's talk about period. What is a period? Okay, well, the period is the time that it takes for one cycle. The time of one cycle is called the period. So you've got wavelength is the length of one cycle. The time for one cycle is called the period. Now I have this down here, and I'm going to explain this part down here for a second. Frequency and period are related. Okay, so remember what frequency was. Let's go back. Frequency is the number of cycles in a given amount of time. So usually in hertz, that is cycles per second. So what we want to understand is that frequency, sometimes it's a lowercase f like this, right? Frequency is cycles per time. So it's the number of cycles in a given amount of time. Period, T, is the time per cycle. So they're reciprocals of each other, and that's where this comes in. And sometimes maybe this isn't great to show right away, but frequency and period here are reciprocals of each other, inversely proportional. So I like showing this probably more than those other formulas. Let's see if I can erase a highlight. I don't know if I can. Apparently not. Let's try that again. Okay, so frequency is in hertz. Okay, the unit is in hertz. If it's per 1 second, and this, the time per cycle, is basically just in seconds. Okay, so the unit is just seconds, or minutes or whatever, but typically it's seconds. Okay. All right, so here's some notes on amplitude. Okay. I'm trying to get too far ahead of me here with these notes. I know I have lots on the screen, but the maximum displacement, if we're talking about a wave, the maximum displacement, so again, that's from that kind of the middle of the wave, or the rest, what would be the rest position. The maximum displacement is called the amplitude. So the distance, as we mentioned there in the diagram, from the rest position to either the crest at the top or the trough at the bottom would be the amplitude. So I'll just draw that again once more in case you want to Get that in. So again, this would be sort of the rest position, right? Middle of the wave. So here is your amplitude here. Right there. Yeah. See, if this is indeed the middle, this distance should be the exact same. Say going up to the crest or going down to the trough. So yeah, you could measure amplitude down as well to the bottom. But just don't measure from the top up here to the bottom. This is not the amplitude. Okay? That's not right. Questions? Okay, you guys doing great. All right. So a wave that consists of a single disturbance. All right, and I've kind of got it drawn down here like this. One single disturbance. And if we're talking about, like a wave like this along a skipping rope or a garden hose, you kind of grab the hose and you kind of go up and down real quick, and that little wave, kind of like a half a wave, kind of travels along the rope or along the hose, you know what I mean? That's called a pulse. So a single disturbance like this will be a pulse. And when we get to have time with the slinkies, you'll be able to do that too. Kind of like go, up, and this wave will travel through along the slinky there. Okay? So this is called a pulse. So this would be the rest position here, and then you have a single disturbance like this. And I put an arrow down here because, as you know, this would travel down the rope or the hose or the slinky or whatever it is, and it would travel in a direction. Okay? So that's called a pulse. Now we'll get back to this diagram here that I showed you earlier, and this talks about the two types of waves that we're going to focus on in the first part of chapter 10 here. So there's two types of waves. And the two main types, one is called transverse wave, and that's this first one down here is the transverse wave. Okay. And you can draw that pretty easily, right? It's just like a wave, like a typical sort of wave that we've been looking at. And the other is called a longitudinal wave. Longitudinal wave. And that's this one down here. This is the longitudinal wave. And what happens here, you see the person making this wave is moving their hand up and down. The person that's making this wave with this little spring here is moving back and forth. Okay? And so what happens is you see, you see sort of compressions here, the really dense parts of the spring, and then you see, really sparse parts, and the wave is actually traveling, in a direction here as well. And so it kind of looks like this. And again, you'll get to see this when we use the slinky, but two very different types of waves. A transverse wave occurs when particles move at right angles to the direction of the travel. Right angles, and the important part here is this right angles. So you can imagine if you had, say, a particle or just something stuck to the slinky, and this person was moving the slinky up and down, and the wave was traveling this way, that this particle is going to be moving up and down as well. Right? Up and down, up and down. And the whole right angles would be, 90-degree angle here. So this is going up and down, and this is going side to side. I'm going to show you a little video here later, real soon as well. Okay? But that's what the right angles mean. Examples are water waves. Okay? Moving a rope or a slinky side to side. Those are examples. Longitudinal waves occur when the particles in the medium move in the same direction as the wave motion. And so if we look at a little particle here on this spring, right, it's here one moment, and then as this person moves their hand in and out, there's these little compressions are moving along, and this thing kind of goes out and then back in, and out and back in. It goes the same direction, parallel, same direction as the wave is moving. Examples of longitudinal wave situations are sound waves. Okay, that's how the particles in the air are moving when I talk. So again, I'm talking and I'm sending out disturbances through the air, and it's the air molecules, the molecules of gas and things that are in the air that are literally bumping into each other, and they're sending that disturbance through the air. And your ears are sensing these small little taps on your eardrum. It's amazing. It's absolutely amazing how that works, isn't it? But because of the way I form my words, there's different pressures on your ear, and your brain interprets those slightly different pressures. It's like a drummer, when they go boom, 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 you can interpret that wave as different than being ba 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 ba, bum bum, ba 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 ba. The speed, yes, but the intensity, right? And so your ears are doing that all the time. And as I form my words, those varying intensities of pressure in your ear, your brain interprets that as words, as language. So it's really, really super cool. But if you think about a sound speaker, okay, you think about a speaker in your stereo system at home, right? It's kind of like conical, right? It's like a cone. And here you go, you got kind of the middle of the speaker here, and it kind of goes out like this, okay, all the way around. And what happens is this part in the middle moves back and forth. Very, very slightly, but very, very fast. And you'll see the cone in the speaker moving back and forth like this. And if you turn up the bass a lot, the bass waves are really long waves, and your speaker really moves in and out like this a lot. Okay? The high frequency waves, the speaker is vibrating, you can hardly even see it. But if you got big, bass going, it's like boom, 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 and you can see that speaker go, right? So that's what's happening. This is pushing the waves so that the air molecules are like bunching up as they push through the medium, and you hear, right? Use your ear, sort of. You hear all this, these waves coming in, or the air molecules coming in. It's like big pressure, not a lot of pressure. Big pressure, not a lot of pressure. Big pressure, and so on. And so that's how you kind of interpret that. But you look at speakers next time, you play in music. They just move in and out really fast. That's all it is. All that music is translated into this vibration. It's really cool. So other examples of longitudinal waves, cars bumping into each other. A pendulum, back and forth, this whole, like this, right? You got all these, hanging down here on the pendulum, right? And they bump into each other, and this sends this one up, and then this one comes back down, bumps into each other, right? And this one comes back up, so on, right? So, that one? Yeah. Okay. All right, good. Okay, we're almost done the kind of the notes for today, and I'm going to show you a video, and then you can read. But as we finish up here, a couple things I want to highlight too. The parts of the longitudinal wave, now I haven't called them by their name yet, but these parts here, the compressions, I told you about compressions. So where the particles are bunched up, okay, where they're bunched up, those are called compressions. So they're the dense areas of particles in that longitudinal waves. And rarefactions, sometimes called expansions, but not very often. Rarefactions is the word. And they are the least dense sections of the wave. So compressions and rarefactions. You think about the word rare, right? It doesn't happen very often, or there's not a lot. It's rare, right? So not a lot of particles. That's the dense part. Okay? So you've got a bunch of particles here, and then it's quite separated, and then there's a bunch of particles here, and quite separate, and so on, right? These are the compressions right here. And these are the rarefactions, the empty spaces right here. So that. Compressions, rarefactions. Okay, so here's a little video on waves. It's only just under 3 minutes, so we'll show it to you here as part of this video. And expert math tutor is is the guy that put this up. So just take a couple minutes and let's watch this video together.
First thing you need to know about waves is there are two different types of wave. One, shown here, by waves in the sea. The other one, shown by sound waves. So how are they different? So first let's look at the sea waves. If we look at them represented in this slinky, we see that the vibrations are at 90 degrees perpendicular to the direction of travel of the wave. These are called transverse waves. Examples of them are waves in water, waves on a string, or light waves. Now let's look at the sound waves again. Again, we see them represented by the slinky. At this time, the direction of vibration is parallel to the direction of travel. These are called longitudinal waves, and the only example you really need to remember is sound. One really important thing to remember about waves is they only transfer energy from place to place, not any matter. You can see that here by looking at a lovely rubber duck sat in a bath. As a wave goes through, the duck bobs up and down, but once the wave's gone, it's back to its original position. The wave has carried energy through, but it did not carry the duck with it. Finally, we need to know some key features of waves. First off, wavelength. A wavelength is the length of a full cycle of a wave, from one point to the next segment. It's easiest to think of as the distance from crest to crest, or from trough to trough.
So one thing we haven't got to yet is the symbol for wavelength, so you might want to jot that down. It's the Greek letter lambda, and it looks just like this. That's the symbol for wavelength. You might just want to jot that down. It's coming later in your notes, but that's what that is. It's a Greek letter lambda. So again, the distance from one crest to the very next crest, or from the start of a wave to the start of the next wave, any of that should be the wavelength. Okay.
Measure it in meters. It's given the symbol lambda. The amplitude is like the size of a wave. But you need to remember that it's measured in equilibrium position in the central line.
Or the rest position there, the central
not
line.
From the crest to the trough. Find the frequency, which is the number of complete waves to pass a point every second. It's given the unit of hertz. So an example of this would be 10 waves passing in 2 seconds, the frequency would be 5 hertz. Using these things, we can actually now calculate the speed of a wave.
So I'm just going to go over that again here.
Calculate the speed of a wave.
Oops.
Using the equation.
Sorry. I'm just going to go over that little calculation again. I think that was fruitful. So you watch the wave pass by and they just count the number of waves to calculate the frequency.
So an example of this would be 10 waves passing in 2 seconds. The frequency would be 5 hertz.
Okay, so you get that? The number of waves per second. Now, this is not per 1 second, but the final answer would be 5 waves per 1 second, right? So when you're doing your calculations, you could have 1,000 waves in 57 seconds. You just do that division, right, to get hertz.
Using these things, we can actually now calculate the speed of a wave. Using the equation, speed equals frequency times wave.
And this is coming up soon in your notes, so you can just listen to this. You might not quite get it right away. We'll do that soon.
So there's a lot to learn here. Once you've learned these core concepts, it will give you much more confidence in the rest of the topic.
All right. Plenty of thanks to my English friend. Don't know his name. Anyways. Expert math tutor. Good job. Okay, so what you guys can do right now is take some time, okay? And I do want it quiet in here, please, so that you can focus. I'd like you to read 10.1 to 10.5. I am giving you some time today in class to do that, so please make good use of it and just kind of get into the habit, into the practice of doing this at home on your own time. You read through, and then you can add in the little notes or the little things that you read about that you maybe didn't get in the lecture, right? So add those things to your notes. So make a complete understanding for yourself. Even if you have questions, write down questions, okay, that you have, that you want to ask me next class, or that you want to talk to your friends about, or you want to look up later, okay? This is all part of just spending time. This is studying, okay? You think about studying as the night before a test. That's not just when studying happens. It can happen every day.